Good morning everyone. In the last class we learnt how to compute Gershgorin bounds which help us to specify the location of the eigenvalues of a given matrix A. So, now we shall consider some examples and see how we can obtain the Gershgorin bounds. Let us start with a simple example of a 2 by 2 matrix A. So, here the matrix A has entries 1, 2, 1 minus 1 and we can actually compute the eigenvalues in this case. The eigenvalues are given by determinant of A minus lambda I equal to 0. So, if you compute the determinant of this matrix and equate it to 0 and solve the corresponding characteristic polynomial for lambda, then you get lambda to be plus or minus root 3. So, you know that one of the eigenvalues of matrix A is plus root 3 and the other eigenvalue is minus root 3. Now, let us apply the Gershgorin's theorem's results and see what information that we get about the location of these two eigenvalues. So, the two eigenvalues plus or minus root 3 have actually been marked on the real line. They are real eigenvalues. I have marked them here by means of star. This is lambda equal to minus root 3 and this is lambda equal to plus root 3. Now, let us use Gershgorin's theorems. So, from the rows of matrix A, I consider the first row, this is A11 and Gershgorin's theorem tell us that modulus of lambda minus A11 which is 1 is less than or equal to sum of the absolute values of the other entries in that row. So, here we have only one element which is 2. So, the first result tells us that absolute value of lambda minus 1 is less than or equal to 2. This gives us one circle and some information about an eigenvalue of the matrix A can be obtained from here. Then taking the second row we have lambda minus of minus 1 which is A22, that is lambda plus 1 in absolute value must be less than or equal to the sum of the absolute values of the other entries. Here in this case it is 1. So, modulus of lambda plus 1 less than or equal to 1 is going to be the second Gershgorin circle that we have. So, we observe that for the matrix A that we have considered, there are now two disks in the complex plane and the center of the disks are A11 and A22 which appear in the matrix A. So, each centered on one of the diagonal entries of the matrix A, and from the theorems we know that every eigenvalue must lie within one of these circles, and however we do not have any information about the fact that each disk contains an eigenvalue. So, this information is not obtained from Gershgorin's theorems. So, let us see another example. So, in the second example again I consider a 2 by 2 matrix. As before, we can consider the eigenvalues of this matrix A. They can be actually computed by solving the characteristic polynomial given by determinant of A minus lambda I equal to 0, and we observe that the eigenvalues are given by lambda equal to plus or minus I. So, those eigenvalues are actually plotted here. This is lambda equal to I and this is lambda equal to minus I. They are marked by star here in the complex plane. Now, let us see what the Gershgorin's theorem tell us. That Gershgorin's theorems tell us that the circles within which the eigenvalues plus or minus I are given by modulus of lambda minus A11 where A11 is 1 is less than or equal to modulus of minus 1, that is 1, and modulus of lambda minus of minus 1, that is modulus of lambda plus 1 is less than or equal to 2, and that gives us the second circle. So, 1 and 2 are Gershgorin's circles and the eigenvalues I and minus I lie in the union of these two circles is what is given by Gershgorin's theorem. And we observe in this case that all the eigenvalues, namely plus I and minus I, lie within the circular disk given by modulus of lambda plus 1 less than or equal to 2, and that is defined by the second row. Right? Let us now consider another example, namely consider a 3 by 3 matrix A, and here Gershgorin's circles theorem tells us that all the eigenvalues lie within the Gershgorin circles given by mod lambda minus phi is less than or equal to sum of the absolute values of the other two entries in the row, and that is 0.7. Then modulus of lambda minus 6, which is this, is less than or equal to sum of the absolute values of the other two entries, that is 1.1. And finally, modulus of lambda minus 2 is less than or equal to 1 plus 0, and therefore we have the Gershgorin's circles are given by these. So, finally we see that the circle which has its center at 2 and radius 2 is disjoint from the other two circles, which clearly tells us that there is exactly one eigenvalue in this circle which is disjoint from the others. And there are two more eigenvalues, and these two eigenvalues lie in the union of other two circles which we have given. And we also observe that all the eigenvalues are real because they have a positive real part. And the second thing is, therefore, the circle modulus of lambda minus 2 less than or equal to 2 is such that it has an eigenvalue which is a real eigenvalue, since complex eigenvalues, if they occur, they must occur in conjugate pairs. And so this circle, the disjoint circle, encloses one and only one eigenvalue which is a real eigenvalue. Now to get more information, we apply Gershgorin's theorems to the transpose of the matrix A, that is A transpose. Then we observe that eigenvalues must lie within the Gershgorin circles which are given by modulus of lambda minus phi less than or equal to sum of the absolute values in the first column, that is 2, and modulus of lambda minus 6 is less than or equal to sum of the absolute values in the second column, which is 0.6, and finally if you use the third column of matrix A, that gives you mod lambda minus 2 is less than or equal to 0.2. Right. So, you observe that this is that disjoint circle with center at the point 2, and this result which is obtained from the columns of A tell us that that single eigenvalue which lies in the disjoint circle must be such that lambda must be greater than or equal to 1.8 and less than or equal to 2.2, and so lambda lies in the interval 1.8 to 2.2. So, it clearly gives you an interval within which this single eigenvalue lies within that disjoint circle. So, we are able to get the location of the eigenvalues of a given matrix A by applying Gershgorin circles theorem in terms of rows and in terms of the columns of the matrix A or the rows of the corresponding matrix which is A transpose. So, we now consider another example in which, say, A is again a 3 by 3 matrix. Immediately we can write down the Gershgorin circles. What are they? They are given by modulus of lambda minus 4 less than or equal to 2 plus 3, which is 5. Modulus of lambda minus of minus 5, that is lambda plus 5, is less than or equal to modulus of minus 2 plus 8, which is less 10, and modulus of lambda minus 3 is less than or equal to mod 1 plus 0, that is 1. So, these are the 3 circles and the eigenvalues of this given matrix lie within the union of these 3 circles. So, you just plot these circles, because you know the center of the circles are going to be respectively 4, 5 and 3. I mean 4, minus 5 and 3, and the radius of the circles are going to be 5, 10 and 1 respectively. So, plot the circles in the complex plane and you know the eigenvalues of the given matrix lie within the union of these 3 circles in this case. So, let us now take another example. So, again A is a 3 by 3 matrix, and it is clear that the eigenvalues of the matrix A lie within the union of the circles mod z minus 15 less than or equal to 4, mod z plus 2 less than or equal to 2 and mod z minus 1 less than or equal to 7. And the one with center at 15 and radius is equal to 4 is going to be a circle which is disjoint from the other 2 circles. So, as before we argue and say, conclude that that circle which is disjoint from the other circles must contain one eigenvalue, and the other 2 eigenvalues lie in the union of the other 2 circles, namely mod z plus 2 less than or equal to 2 and mod z minus 1 less than or equal to 7. So, the Gershgorin's theorem is very useful in understanding the location of the eigenvalues of a given matrix A. So, let us look into another example. Suppose A is given by this 3 by 3 matrix. We can write down the Gershgorin circles. So, mod lambda minus 4 is less than or equal to 1, mod lambda minus 0, that is mod lambda less than or equal to 2, and mod lambda plus 4 is less than or equal to 2. So, these are the circles which we have plotted here, and we observe that this circle 1 is disjoint from the other 2 circles, and therefore, it must contain a single eigenvalue within it. And we also observe that if we write down the characteristic polynomial, the coefficients of the characteristic polynomial given by determinant of a minus lambda I equal to 0 are real, and hence the complex values which are eigenvalues, if they occur at all, then they occur in conjugate pairs. Therefore, there is a single real eigenvalue within this interval, namely 3 to 5, because this is a disjoint circle, right. A single eigenvalue lies within it and the radius of the circle is 1. So, that single eigenvalue is real, and that real eigenvalue lies between 3 and 5. So, we know the interval within which this real eigenvalue lies. And then the other 2 circles, so the other 2 eigenvalues lie in the union of these 2 circles is what we know. But we observe that these 2 circles meet each other or touch each other at the point minus 2. So, we would like to see whether minus 2 is an eigenvalue of the matrix A. How do you check whether lambda equal to lambda naught is an eigenvalue of a matrix A? You just have to see whether it is a root of the characteristic polynomial determinant of a minus lambda I equal to 0. That is what you have to check. So, let us compute determinant of lambda minus a minus lambda I, taking lambda to be minus 2. So, if you write out the determinant and expand, and you observe that that turns out to be minus 17, which is different from 0, and therefore, the characteristic polynomial does not have lambda equal to minus 2 as its root, and therefore, lambda equal to minus 2 is not an eigenvalue of the matrix A, is what we conclude. What does it mean? We said earlier that the other two eigenvalues lie in the union of those two circles, and the point where they touch each other, namely -2, is not an eigenvalue, alright, and therefore the other two eigenvalues must be such that each one must lie in each of these circles, and that is the conclusion that we get from our discussion. So, there is one eigenvalue in the interval -6 to -2 and another eigenvalue which is in -2 to -2. Why does that happen? So, let us look at the circles. So, this is a circle with center at -4 and radius 2, and therefore, it passes through the points -6 and -2. So, one of the eigenvalues lies between -6 and -2, and you have another circle whose center is origin and radius is 2 units, and there is an eigenvalue within this circle and it is a real eigenvalue, and therefore, it lies between -2 and 2. So, the matrix A is such that it has one real eigenvalue between -6 and -2, another real eigenvalue between -2 and 2, and a third real eigenvalue between 3 and 5. And so, we conclude that A has one eigenvalue in each of these intervals -6 to -2, -2 to 2 and 3 to 5. So, information about the location of the eigenvalues can be obtained by writing out the Gershgorin's circles within which the eigenvalues are located and arguing out depending upon whether these circles are disjoint or the eigenvalues lie within the union of these circles and so on. So, now we have another problem where A is a matrix, say it is an n cross n matrix having entries given by these, namely along the diagonals you have 4 appearing throughout, and just above the diagonal entries have value 1, and just below the diagonal the entries are again 1. The rest of the entries are all zeros. So, you have an n cross n matrix where Aij are given by the entries which are specified here. You are asked to show that the inverse of this matrix A has its eigenvalues in the interval 1/6 to 1/2. So, you need some information about the location of the eigenvalues of the inverse of this matrix A. We have already seen while doing the Gershgorin's theorems and other details, we have remarked that if lambda is an eigenvalue of A, then 1 by lambda is an eigenvalue of A inverse. We have actually shown this result. So, now we want to show that A inverse has its eigenvalues in the interval 1/6 to 1/2. So, let us first determine the interval within which eigenvalues of A lie, and then we can use this result and make a conclusion about the location of eigenvalues of the matrix A inverse. First of all, we observe that A is a symmetric matrix, Aij is Aj. So, what do you immediately conclude? All its eigenvalues are going to be real, namely all the eigenvalues of matrix A are going to be real. That is the first information that we get by looking at what the matrix A, and the matrix A is symmetric. Now, let us apply Gershgorin circles theorem to the rows of this matrix A. So, every row has 4 along its diagonal, and therefore, the Gershgorin circles will be given by modulus of lambda minus 4 is less than or equal to sum of the absolute values of the entries in that row, and we observe that the first row has entry to the right of 4. So, the first row will give us the Gershgorin circle to be mod lambda minus 4 less than or equal to 1. Similarly, the last row will give us mod lambda minus 4 is less than or equal to 1, because the rest of the entries are all zeros. Now, apply Gershgorin's theorem to all the other rows starting from the second row to the n minus 1th row. We observe that the diagonal entries are 4 and you have on either side of the diagonal entry value 1 appears to the right of it and value 1 appears to the left of it, and hence we get modulus of lambda minus 4 less than or equal to 2 to be the Gershgorin circles. So, what does this mean? If you write out this tells you minus 2 less than or equal to lambda minus 4 less than or equal to 2, and therefore, that immediately tells you that all the eigenvalues lie in the interval 2 to 6. So, what are these eigenvalues? They are the eigenvalues of matrix A. So, Gershgorin circles theorem tell us that all the eigenvalues of A are real and all the eigenvalues of the matrix A lie within the interval 2 to 6. So, now we make use of the result that we have shown. What is it? Eigenvalues of A inverse are reciprocals of eigenvalues of A. So, A has eigenvalues lying in the interval 2 to 6, and therefore, if mu denotes the eigenvalues of A inverse, then mu has to lie between the reciprocal of 2 and reciprocal of 6, namely mu has to lie between 1 by 6 and 1 by 2. So, mu lies between 1 by 6 and 1 by 2, and therefore, the conclusion is that all the eigenvalues mu of A inverse lie in the interval 1 by 6 to 1 by 2, and that is what we are asked to show, right. So, we have made use of the two results. What are the two results? We said that if A is a symmetric matrix, all eigenvalues are real, and secondly, we use the fact that eigenvalues of A inverse are given by the reciprocals of eigenvalues of A. So, we first computed the eigenvalues of A and then we used the result and got some information about the location of the eigenvalues of the matrix A inverse. So, these are some examples in Gershgorin's theorems and location of eigenvalues of a given matrix. Now, we move on to some examples where we discuss the computation of norm of a matrix and then some problems from the error analysis by the direct methods of solving a system of equations Ax is equal to b. So, suppose I give you a matrix A which is this and I make a statement. I make the statement that the matrix A given by this is ill conditioned, and I ask you to tell me whether this statement is true or false. It is just not enough if you say that the statement is true or the statement is false. You have to justify your statement whether it is a true statement or a false statement. Then only your answer will be correct and you have justified your conclusion. So, how am I going to conclude whether the statement is true or false? How do I say or how do I find out whether the matrix is an ill conditioned matrix or not? I compute what is its condition number. If the condition number is very large, then we conclude that the matrix A is ill conditioned. So, I compute the condition number, and what is the condition number? Condition number is norm A into norm A inverse. So, given a matrix A, I compute its inverse and then I compute norm of A, then norm of A inverse, and then find what K of A, the condition number of A is. So, I compute norm A using maximum column sum norm. So, I have it maximum of 100 plus modulus of minus 200, so 300, then modulus of minus 200 plus 401, that is 601. So, norm A is 601. So, with respect to the maximum column sum norm, norm A is 601. Now, I compute norm A inverse with respect to the maximum column sum. So, norm A inverse is going to be equal to maximum of the sum of the absolute values of the entries in the first column, which is 6.01, and the sum of the entries in the second column after taking the absolute value, right, and that gives you 3, and so it is 6.01, and therefore norm A inverse is 6.01. So, now compute the condition number of A. It is norm A into norm A inverse. So, that is 601 into 6.01, and it turns out to be 3612, which is very much greater than the value 1, right. For a well conditioned system, the condition number must be close to a value 1 greater than 1, and here it turns out to be 3612, and therefore A is an ill conditioned matrix. So, the statement that has been given, namely the matrix A is ill conditioned, is a true statement. So, whenever you are given some statement and we are asked to check whether the statement is true or false, right, in order to conclude what the answer is, you must work out the details, and based on the results that you get, you must conclude whether the statement is true or false, in which case you have justified your conclusion. So, let us now consider an example where we want to perform some error analysis. Suppose say you are given epsilon greater than 0 and a matrix A having entries 1, 1 plus epsilon in the first row and 1 minus epsilon and 1 in the second row. Immediately I can compute A inverse, and that is given there. And this time I would like to obtain norm of A using the infinity norm. So, what is the condition number is norm A infinity into norm A inverse infinity, and that turns out to be 2 plus epsilon the whole square by epsilon square. So, this is surely greater than 4 by epsilon square. If suppose in the matrix that is given, I take my epsilon, which is positive, to be such that it is less than or equal to 0.01. Then I observe that in that case K of A is greater than 4 by 0.01 the whole square, and that will turn out to be 40,000. So, K condition number of A will turn out to be greater than or equal to 40,000, which is a very large quantity. Suppose I give a small change in one of the entries in the matrix A, namely I add epsilon to this entry and subtract epsilon from this entry. So, if I perturb entries in the given matrix A, then what happens to the condition number? In that case, the condition number becomes very large, and so this says that a relative perturbation in the right hand side may induce a relative perturbation 40,000 times greater in the solution of the given system Ax is equal to B. So, change in some entries in A will give the corresponding changes in the solution, and that is going to be such that it is going to be 40,000 times greater in the solution of the given system Ax is equal to B. So, let us now consider what happens if we want to compute the condition number of a matrix A, which is a 3 by 3 matrix using the maximum absolute row sum norm. So, A is given. So, you can compute A inverse using Gauss-Jordan technique. Now, you have learnt that. So, you know how to compute the inverse of a given matrix using Gauss-Jordan technique. And now, you compute norm A infinity. What is it? It is maximum absolute row sum norm for A. So, it is the maximum of sum of the entries in each of these rows after taking the absolute values, and that turns out to be maximum of 14, 29 and 50, and that is 50. Now, compute norm A inverse infinity. Here again I want to use the maximum row sum norm, and so compute the sum of the entries in absolute values in each of the rows, and from among them choose that which is the maximum. That turns out to be 15. So, norm A inverse infinity is 15. So, the condition number of a given matrix A is K of A given by norm A infinity into norm A inverse infinity, which is 50 from here and 15 from norm A inverse infinity. That gives you 750. So, we can say that the matrix A is an ill-conditioned matrix. Now, I consider another example. Taking A to be a 2 by 2 matrix, and I want you to compute the condition number of A with respect to the 2 norm. So, when I work out the 2 norm for the matrix A, that turns out to be 3.165. I also require the 2 norm for A inverse, because I am asked to compute the condition number of A. So, norm A inverse 2 turns out to be 158.27. Now that you know the definition of 2 norm for a matrix A, you can compute A inverse and work out the details and show that norm A inverse 2 is 158.27, and therefore, the condition number is norm A into norm A inverse with respect to the 2 norm, and so it is the product of these 2 values, and that turns out to be this. So, you have actually computed it and you are asked to fill in the blanks here. So, write out the result here that it is 500.974, and you observe that this is a large quantity, and therefore, you are asked to make some conclusion about what the matrix is. And you know, since the condition number is large, the matrix is ill conditioned. So, you fill in the blanks here by saying that the matrix is an ill conditioned matrix. Compute the condition number of the following matrix relative to infinity norm. So, A is a 2 by 2 matrix. Norm A infinity is maximum row sum. So, compute the row sum, namely the first row sum in absolute values and the second row sum, and you conclude that norm A infinity turns out to be this. Now, what is the determinant of A? That turns out to be 1 by 72. Get A inverse and work out what norm A inverse infinity is. Again, maximum row sum norm is used, and so you have maximum of 42 and 60 to give you norm A inverse infinity, and that turns out to be 60. So, what is the condition number? The condition number is norm A infinity into norm A inverse infinity. We have computed each of these. So, the product of this gives you norm A infinity into norm A inverse infinity, and that is 50, and you are asked to get what the condition number is. So, the condition number of A is 50. So, now we know how to compute norm of a vector or norm of a matrix associated with the norm of a vector which is given. So, let us work out some details about the error analysis for direct methods. So, the problem is the following linear system Ax is equal to B has x as the actual solution, and x tilde is an approximate solution. So, you are asked to compute the magnitude of the absolute error and also compute what is the residual, namely norm of Ax tilde minus B with respect to the infinity norm. So, you are given a system of 2 equations in 2 unknowns, and you observe that these coefficients half, 1 by 3, 1 by 3, 1 by 4 are the same as the example which we have considered earlier, and x is equal to 1 by 7 minus 1 by 6 transpose is the actual solution, and x tilde, which is this, is an approximate solution. So, solve this system say by applying Gauss elimination method with partial pivoting and get the solution correct to 3 decimal places, and that is what is your x tilde. So, now you want to compute the error. What is the error? It is x minus x tilde. So, x is 1 by 7, x tilde first component is 0.142. Second component is minus 1 by 6 and the second component of x tilde is minus 0.166. So, it is this quantity and you want norm x minus x tilde infinity. So, it is the maximum of the first entry and the second entry. So, maximum of absolute value of the first entry and the absolute value of the second entry. So, compute this. So, you get this to be maximum of this and this, which turns out to be the value 0.0085714. So, that is the absolute error in the solution x of the system Ax is equal to b. So, you would like to find what is the residual. So, compute A into x tilde. So, A matrix is given, x tilde is given. So, work out what is A into x tilde, which turns out to be this vector. So, what is the residual? Residual is Ax tilde minus b. Why is it a residual? You want x to satisfy the equation Ax is equal to b. So, Ax minus b must be 0. But x tilde is an approximate solution. So, Ax tilde minus b will not be equal to 0, it gives you a residual and so you call R as Ax tilde minus b. So, you computed Ax tilde as this, so that vector minus you know what the right hand side vector is. So, substitute that and then evaluate what is the difference and compute norm Ax tilde minus b, that is the maximum of the absolute values of the entries that you have written here and that turns out to be 0.0020635. So, you will be in a position to compute the absolute error which is norm x minus x tilde as well as the norm of the residual R which is norm Ax tilde minus b with respect to any norm that will be asked. In this example, you have been asked to get these values using the infinity norm and you have computed them with respect to infinity norm. And now you are asked to compute the condition number relative to infinity norm and also the condition number times the residual by norm A with respect to infinity norm. So, you compute what is condition number. It is norm A infinity into norm A inverse infinity. We already have computed the condition number earlier when we worked out the example. It turned out to be 50 and now we have computed what is the residual, namely norm B minus Ax tilde with respect to infinity norm and that is 0.0020635. And we also have computed norm A with respect to infinity norm which is this. So, we simply have to substitute these values which appear on the left hand side, namely these, and then simplify and that gives you the value of this, namely condition number multiplied by norm of the residual by norm A infinity to be equal to this. If we know how to compute the matrix norm given the vector norm, then we will be in a position to compute the absolute error and also the relative error. So, that is what is given in the next example. Suppose that x tilde is an approximation to the solution of Ax is equal to b. A is a non-singular matrix and R is the residual vector for x tilde, that is R is Ax tilde minus b. Then you are asked to show that for any natural norm, namely infinity norm or 2 norm, you should be able to show norm x minus x tilde is less than or equal to norm R into norm A inverse. And in addition, if x is different from 0 is a non-zero vector and b is also a non-zero vector, then show that the relative error in our computation. What is the relative error? It is change in x with respect to x. So, it is norm x minus x tilde by norm x, that must be less than or equal to the condition number, which is norm A into norm A inverse multiplied by the norm of the residual by the norm of the right hand side vector. This is what we have to show. So, these two results clearly tell us the bound on the absolute error, namely this is the right hand side, your absolute error cannot exceed the value on the right hand side. Your relative error in the computation of solution of a system Ax is equal to b cannot exceed the value on the right hand side. What is it? It is condition number of the matrix A times the norm of the residual by norm of the right hand side vector b. So, let us work out the details. Now, residual is r, which is b minus Ax tilde. But what do you know about b? B is Ax. So, it is Ax minus Ax tilde, that is A into x minus tilde. So, I pre-multiply both sides by A inverse, because it is given A is a non-singular matrix. So, A inverse exists and therefore, I multiply by A inverse. So, we have A inverse into R to be A inverse A into x minus x tilde. So, that will be x minus x tilde, and therefore, norm x minus x tilde will be norm of A inverse into R. But we have shown already norm of A B, where A and B are matrices, will be less than or equal to norm A into norm B. So, let us make use of that result. So, norm A inverse R is less than or equal to norm A inverse into norm R. So, this proves our first result. That is what we have to show, namely norm of x minus x tilde is less than or equal to norm R into norm A inverse, and we have shown that result 1. Now, we know that B is Ax. So, norm B is norm Ax, that is less than or equal to norm A into norm x, and therefore, 1 by norm x is less than or equal to norm A divided by norm B. Now, consider norm x minus x tilde less than or equal to norm A inverse into norm R, and therefore, divide by norm x throughout. So, you get norm x minus x tilde by norm x is norm A inverse into norm R, and what about norm x? We know Ax is B. So, I also know norm B is less than or equal to norm A into norm x, and so I can replace 1 by norm x by a quantity which is less than or equal to norm A by norm B. So, I replace this 1 by norm x by this, and this gives me norm A inverse into norm A into norm R by norm B, and that is what we have to show here, namely norm A inverse norm R. We can immediately get the bound on the absolute error and the relative error. For a given problem, when we get an approximate solution using the direct methods, namely Gauss elimination methods or any of the direct methods that we have studied. So, given a system Ax is equal to B, and if you apply direct methods to solve this system, then you can immediately specify the amount of absolute error and relative error that are involved in your computations by using the bounds which are given by these examples. What is it that we have done all along in this course? We have focused our attention on 5 important topics which are very useful to us in obtaining approximation of a function whose values are specified at discrete points. Namely, we discussed polynomial approximation, and then when the information is given at a set of equally spaced points, we used Newton's forward interpolation polynomial or backward interpolation polynomial and obtain an approximate polynomial, namely the interpolating polynomial that interpolates the function at a set of given points. If the information is given at a set of arbitrarily located points, then we had Lagrange interpolation method and divided difference method to compute the interpolating polynomial that interpolates the given data, and we have discussed error in interpolation and also the bound on the error in interpolation. Then we considered the topic on numerical differentiation. So, there we derived finite difference approximations to various order derivatives, which can be given in terms of the values of the function at a certain set of points. So, let us consider an example here. Suppose say I give you a formula which approximates the second derivative, f double dash of xi is given by this, and I ask you the following: show that the truncation error in the 4-point backward difference formula which is given by this, that is used to approximate the second derivative, is it order of h, order of h square, or order of h cubed, or order of h to the power of 4. I ask you to choose the correct answer from the 4 choices which I have given here. Unless you work out the details, you will not be able to give the result. So, you start with the right hand side, expand using Taylor's theorem and get the coefficient of fi, f dash I, f double dash I, f triple dash I, and the 4th derivative of I, and so on. And then that is equal to f double dash I, which appears on the left hand side. So, collect the coefficients of fi, you will see it is 0, f dash I, that is also 0, f double dash I also turns out to be 0, f triple dash I also turns out to be 0. On the other hand, the 4th derivative of I coefficient turns out to be different from 0, and so you have right hand side has h power 4 into 4th derivative at I divided by h square, because your formula had 1 by h square in it. So, you observe that you have the 4th derivative term appearing multiplied by h power 4 by h square, and that is a non-zero term. So, it is h square times the 4th derivative, and so that is the first term which is a non-zero term that appears in this formula when you approximate the second derivative by means of the formula on the right hand side. So, you conclude that the truncation error is of order of h square. And we have also discussed after numerical differentiation some results on numerical integration, where we derived the closed type formulas which are Newton-Cotes type formulas, namely the trapezoidal rule and Simpson's rule, and we derived certain integration methods which are exact for polynomials of degree n when we use n nodes in the interval say a b, which is a closed interval. Then we said that if we can sacrifice the requirement that these n nodes are equally spaced and look for methods which are quadrature methods such that they are exact for polynomials of degree greater than n when n nodes are used within an interval of the form a b, in particular an interval of the form -1 to 1, then we said that we obtain open type integration methods where we have used properties of the Legendre polynomials, and the integration methods turn out to be methods which are exact for polynomials of degree less than or equal to 2n minus 1, where the function values at only n nodes are required. And these n nodes turned out to be the zeros of the Legendre polynomial of degree n, and these formulas were of the open type. The nodes were all within the interval -1 to 1. And then we moved on to the solution of ordinary differential equations, where we derived some single step methods like Taylor series method, Euler's method, modified Euler's method, and Runge-Kutta methods of order 2 and 4, and solved an initial value problem using any of these methods. Then we said that it is possible to consider iterative type of methods where we have a predictor to predict the solution and then a corrector which would recorrect the solution, and so that we can obtain solution correct to the desired degree of accuracy. And these methods involved a number of points close to the point at which the initial condition is specified. So that information at 4 points were used to compute the solution at the 5th point, and these were multi-step methods which we used as predictor corrector methods, and we had solved an initial value problem using Milne's predictor corrector and Adam Bashforth's predictor corrector methods. Then we moved on to solution of nonlinear equations of the form f of x is equal to 0. So, we discussed two types of methods, namely the enclosure methods and then the fixed point iteration method, and discussed the order of convergence of these methods, and we learnt some techniques of solving equations of the form f of x is equal to 0. And finally, we moved on to the solution of a system of algebraic equations, and then discussed the direct methods and iterative methods. And the direct methods included the decomposition methods of Doolittle, Kraut and Cholesky, and Gauss elimination method incorporating partial pivoting. And then we discussed the iterative methods such as Gauss-Seidel method and Gauss-Jacobi method. But then we wanted to see how in the case of direct methods we can have some information about the error that has been committed by us. So, we performed error analysis, and so we introduced norm of a vector, norm of a matrix associated with the given norm for a vector, and we have shown how to get a bound on the absolute error and the relative error when we know the condition number of a given matrix A, which appears as the coefficient matrix in the system Ax is equal to B, and when we know what the norm of the residual, which is norm A x tilde minus B, where x tilde is an approximate solution and B is the right hand side vector that appears in the system Ax is equal to B. And finally, we moved to the matrix eigenvalue problems and computed the most dominant eigenvalue by power method, and discussed the Gershgorin bounds using Gershgorin's circle theorem and Brouwer's theorem. And we have illustrated all these methods which we have learnt in this course by means of some examples, problems, and you have solved a number of assignment problems. You also have looked into a number of problems which were given to you for practice, and finally you are ready to appear for the end semester examination. The type of problems that you will get in your end semester will be such that you will have questions where you may have to choose the appropriate answer with proper justification. You may have to choose whether a given statement is true or false. You may have to fill in certain blanks where you may have to work out the details first and then fill in the result in the blank, and there will also be problems where you will have to completely work out the details and present the solution. Some questions similar to what may come in your examination, I have included a few examples here. So, let us quickly go through them. So, you have the first question to be choose the appropriate answer. So, you are given a function f of x is interpolated at n plus 1 points x naught to xn. The error in interpolation at any point x which does not coincide with any of the xi for I is equal to 1 to n depends on what is the question. The answer is it dependent on the method that is chosen for interpolation? Surely not, it is clear. Does it depend on the value of the function f at x? No, you do not even know what the value of f at x. Thirdly, is it dependent on the location of x in the interval? No, not at all. X can be anywhere in the interval x naught to xn. Is it dependent on the number of data points? Yes, of course. If you choose 3 points from the data, you can give an interpolating polynomial of degree 2. If you choose 10 points from the data, you can get an interpolating polynomial of degree n. So, the error in interpolation depends on the number of data points and not on any of the other 3 statements which are given. So, you conclude that the result is only on the number of data points and mark D to be the correct result and giving the reason for that. Then you have another question which comes in interpolation again. In which of the following polynomial interpolation methods can one use all the previous computations when new data points are included? We have already discussed this in the class and therefore, I straight away go to the answer. We know that we use in divided difference method all the computations that have been used earlier, because suppose say we are given 3 points and we are asked to get the divided difference interpolation polynomial, then we would be getting the interpolating polynomial of degree 2 that interpolates the set of given data which are 3 in number. But now suddenly I have another information coming about this function. So, another point and the value of the function at that point is given. Now, I have 4 points. So, I can get an interpolating polynomial of degree 3 which I call as P3. Then what is P3? P3 is simply P2 of x, namely the quadratic interpolation polynomial that we already have computed. So, P2 of x plus an extra term, that extra term which arises due to the new information that is given to us. Right, and you know what the extra term should be. So, if x0, x1, x2 are the previous points and x3 is the new point, then the extra term is going to be plus a times x minus x0, x minus x1, x minus x2. How do you determine a? So, your P3 of x is P2 of x plus a times x minus x0, x minus x1, x minus x2. How do you determine a? This P3 must be such that it should interpolate at the new point that is given. So, substitute the x value as the x coordinate of the new point that is given and the y value as the function value that is specified and determine a, and you now have a cubic polynomial which interpolates the given data where you have used the computation of P2 of x which you have already done. So, it is in the divided difference formula that you are able to use the previous computation. So, you write the result is B, that is so in divided difference method. So, you have another problem on divided difference formula which you can try to work out. Now, if I consider examples in say the methods of solving a nonlinear equation of the form f of x is equal to 0, and I say I apply Newton-Raphson method to solve this equation. And the computations are started with an initial approximation P0 close to 2, that is an initial approximation to a root of the equation, and you are asked to find what is limit n tending to infinity of modulus of xn plus 1 minus p by modulus of xn minus p the whole square. Immediately you recognize that this is your error at the n plus 1 step. This is your error at the nth step. So, you are asked to get what is limit as n tending to infinity of en plus 1 by en square. Is it any one of these values? Unless you work out, you cannot give the answer. So, let us work out the details. What is it? I start with en plus 1 by modulus of en square. We have already done error analysis and we have shown when we apply Newton-Raphson method, en plus 1 by en to the power of alpha, where p is an approximation, is nothing but half of the second derivative of f at the root which is p divided by the first derivative of the function at the root. So, p is given because it says close to 2, that information is given to us. So, p is 2 and therefore, we take this value, we know the function. How do we know the function? We are given f of x is equal to x square minus 4. Compute the second derivative, compute the first derivative, substitute these derivatives, evaluate it at 2 and give the values here, and that gives you 1 by 4. So, immediately you know that the answer C is correct, because you have been able to show that it is equal to 1 by 4. And because the Newton-Raphson method is such that the error at the n plus 1 step is given by C into the error at the n step square, where C, the asymptotic error constant, is given by this information, and that result has been used. So, all the results that we have shown in the theorem are very important, in the sense that those results, like what we have now shown, those results can be used to solve some examples, and that has been illustrated above. Let us consider this example. Newton-Raphson method for finding the square root of a real number r. What is it? Is it any one of these is the question. Yes, take the Newton-Raphson method, take the function, you want to get the square root of a real number r. So, what is the equation that you want to solve? X square minus r equal to 0 is the equation. Call that as f of x. So, find f dash of x. Substitute in xn plus 1 equal to xn minus f of xn by f dash of xn. That is what appears here. Substitute, simplify, and you end up, and you observe that that appears here, where in this half of xn plus r by xn. So, you mark C is the correct answer. Similarly, I have another example where we say that we want to compute the reciprocal of a positive real number n using Newton-Raphson method, starting with an initial approximation. So, the sequence of iterates are generated from which one of these? So, we are asked to do by Newton-Raphson method. You want to get the reciprocal of a number. So, the equation that you want to solve is x is equal to 1 by n, or the equation is n minus 1 by x is 0. Compute f dash of x, substitute in Newton-Raphson method, xn plus 1 equal to xn minus f of xn by f dash of xn, and that gives you this, and that appears as one of the results, namely C, and so you can fill in and say that the answer is C. Then we have a result which says, state with reason whether the following statement is true or false. So, the statement is, a nonlinear equation f of x is equal to 0 is solved by bisection method. So, it is a direct method for solving an equation of the form f of x is equal to 0. It belongs to the class of enclosure methods. Now, if the number of steps to be taken, so that you want to get an error of E, and that is n steps with initial interval a b, and you divide the interval in such a way that the length of the initial interval is divided by 3, and the number of steps that you need to commit the same error E is, say, n1. Then the statement says n1 has to be greater than n. Is your statement correct is the question. So, do not worry about what you should write, start writing down what is given. What is given? We know that the error is in bisection method given by the length of the interval by 2 to the power of n plus 1 at the end of n steps. So, use that. Then what do? You divide the interval by 3. So, what is the length of the interval now? It is b minus a by 3. So, what is the error at that step? It is b minus a by 3 divided by 2 power, now the number of steps is n1. So, 2 power n1 plus 1. But what is the error that you commit? It is the same E. So, I have written whatever that is given in the problem. Now, I divide one by the other, and I see that when I take logarithm with respect to base 2, n turns out to be n1 plus some quantity. So, n is bigger than n1, so n is greater than n1. The question says n1 is greater than n. No, the statement is therefore false. Why? Because of all this. So, you have to justify by giving the details of why you are saying that the statement is false. Then, suppose say f is a continuous function on the interval minus 1 to 2. and f of minus 1 into f of 2 is less than 0. What does it mean? A root lies in minus 1 to 2. The number of iterations that are necessary to guarantee that an approximation to a root of f of x equal to 0 using bisection method is correct to within 7 decimal places is what? Which one of them is correct? So, you have a formula which says b minus a by 2 power n plus 1. You want it to be less than half of 10 to the power of minus 7, because correct to within 7 decimal places is what your requirement is. Simplify and you get n to be bigger than 24.84, and you observe that n greater than n is equal to 25 is what appears here. So, now the order of convergence of an iteration method for solving f of x is equal to 0 in a b, if the iteration method generates successive iterates given by xn plus 1 equal to 1 by n plus 1 the whole square, and xn converges to 0 is what? So, you are asked to get the order of convergence of a method. You are given a sequence that generates the successive iterates and which converges to 0. So, what is the order? So, Pn is given. How do you compute the order? You must get what is En plus 1 divided by En power alpha, that must be an asymptotic error constant times, right, En asymptotic error constant, which is C. So, I repeat again, you have to show that En plus 1 is equal to En to the power of alpha multiplied by C. Alpha gives you the order of convergence of the method and C gives you the asymptotic error constant. So, let us see what is this in this example. Now, the sequence converges to 0. So, it is Pn plus 1 minus 0 is En plus 1, Pn minus 0 is En. So, I consider mod En plus 1 by mod En power alpha. So, it is given 1 by n plus 1 the whole square by 1 by n square the whole square. So, that is n to the 1 by n square to the power of Pn power alpha. So, this must be alpha. So, that gives you n power 2 alpha by n plus 1 the whole square. This is alpha, right. So, you have n power alpha by n plus 1 the whole square. Now, when will this quantity converge to 0? That will converge to 0 if alpha is less than 1. It will converge to 1 if alpha is 1, and it will diverge if alpha is greater than 1. And you want the sequence to converge. So, alpha must be such that it converges to 1 if alpha is equal to 1. So, modulus of Pn plus 1 must be C into modulus of Pn to the power of alpha, with C is equal to 1 and alpha equal to 1, and so you conclude that the method converges and its order of convergence is 1. So, it has linear convergence. I have illustrated some examples from the different topics that we have discussed in our course, so that one can expect questions of this type also in your examination. So, I hope you have enjoyed this course and you have learnt some good portion of the topics from numerical analysis from this course, and I wish you all the best in your career and in future. Thank you very much.